Hello students, today we are going to discuss NCERT section 10.1 and 10.2 of chapter Wave Optics. So let's begin. This is the disclaimer. So what should be the comparative strategy for chapter Wave Optics? Let's see, our first focus will be on Huygens principle, which is fundamental to understanding how waves propagate. Remember, this principle helps us visualize wavefronts and predict how waves will behave when they encounter obstacles. Focus on wave nature of light and the different types of wavefronts. This is crucial because it sets the stage for understanding more complex phenomena like interference and diffraction. Think of wavefronts as the shape of the wave as it moves through the space. Have clear understanding of three key phenomena: interference, diffraction, and polarization. These are essential concepts in wave optics that explain how light behaves in various situations. For example, interference is why we see colorful patterns in soap bubbles, while diffraction explains the bending of light around corners. It's important to memorize some key formulas related to these phenomena. For interference, focus on path difference and fringe width. In diffraction, remember angular width and resolving power. For polarization, Malus law and Brewster's angle are critical. These formulas will help you solve problems and understand the underlying physics. To solidify your understanding, practice solving problems from past JEE and NEET papers. This will not only test your knowledge but also prepare you for exams. Remember, practice is key to mastering these concepts. Finally, for additional resources and guidance, visit https://forum.pruter.ai. This platform offers book recommendation and expert advice to further enhance your learning. We will continue to build on these concepts in our further session. So by the end of this session, you will have a solid understanding of the key concepts and historical developments in the theories of light. We will start by looking at the objectives for today, which will guide our learning journey. So you will be able to understand the historical development of light theories, focusing on the debate between the corpuscular theory and the wave theory. Pay special attention to Huygens principle, which is crucial for understanding how light behaves as a wave. This principle explains wavefront propagation, a fundamental concept in wave optics. Moving on to the second objective, you will learn the different types of wavefronts: spherical, plane, and cylindrical. Understanding how these wavefronts form and propagate is essential for grasping various optical phenomena such as reflection, refraction, interference, and diffraction. So we'll start with an introduction to the topic, setting the stage for our exploration of how light behaves as a wave. This is crucial because understanding wave optics allows us to explain phenomena like interference and diffraction, which are not covered by ray optics. Next, we will discuss NCERT section 10.2 Huygens principle. This concept helps us understand how waves propagate and interact with obstacles. Our main objective is to understand the different theories of light that have been proposed over the centuries. This sets the stage for exploring how our understanding of light has evolved. So in the 17th century, two major theories about the nature of light emerged. Let's take a closer look at those foundational ideas. This was a pivotal time in physics as scientists were trying to explain how light behaves. The first theory is the corpuscular theory, proposed in 1637. This theory suggested that light is made up of tiny particles or corpuscles. It's important to note that this idea was supported by famous scientists like Isaac Newton, who believed that these particles traveled in straight lines. The second theory is the wave theory, introduced in 1678. This theory posits the light behaves like a wave, similar to ripples on a pond. Okay, water ripples. This was a revolutionary idea at the time and laid the groundwork for our modern understanding of light. We will explore how these theories compare and contrast in future discussions. Now we are going to explore the corpuscular theory of light. This theory was an early attempt to explain the nature of light, and it laid the groundwork for future discoveries. Let's start with the origin of corpuscular theory. In 1637, René Descartes introduced this model, suggesting that light is made up of tiny particles. Isaac Newton further developed the corpuscular model, which is why this theory is often associated with him. Newton's contributions were significant in popularizing the idea that light consists of particles. Because of Newton's influence, the corpuscular theory is frequently credited to him. According to corpuscular theory, light is composed of tiny, massless, elastic particles called corpuscles. This concept was an attempt to explain how light behaves in different situations. The corpuscular theory successfully explained phenomena like reflection and refraction. However, it struggled to account for interference, diffraction, and polarization. These three phenomena we are going to discuss in wave optics, which are key aspects of wave behavior. The theory also proposed that light bends towards the normal and travels faster when entering a denser medium. This was an attempt to explain refraction using the particle model. While it's true that light bends towards the normal in denser medium, the idea that its speed increase was incorrect. This misconception was later corrected by the wave theory of light. The assumption that light travels faster in a denser medium persisted until the wave theory gained acceptance. This transition marked a significant shift in our understanding of light's nature. Here our objective is to delve into the wave theory of light. This theory is crucial for understanding how light behaves as a wave, which is fundamental to the fields of the wave optics. So in 1678, the Dutch physicist Christian Huygens proposed this theory. It's important to note that Huygens was pioneer in this field, and his ideas laid the groundwork for our modern understanding of light as a wave. According to wave theory, light propagates as a wave. This means that light travels in a manner similar to waves in water, with crests and troughs. This concept helps explain many of the phenomena we observe with light, such as its ability to bend and spread. The wave theory can explain several key phenomena: reflection, refraction, interference, and diffraction. Each of these involves the interaction of light waves with surfaces or other waves. For example, interference occurs when two waves meet and combine, either amplifying or cancelling each out. An interesting prediction of the wave theory is that when light refracts, if it bends towards the normal, the speed of the light is slower in the second medium. This prediction was in direct contradiction to the corpuscular model of the light, which suggested that light particles would speed up in the denser medium. This discrepancy was a significant point of debate at that time and ultimately led to further investigations that supported the wave theory. So we are focusing on why the wave theory of light wasn't immediately accepted. Our objective is to explore the initial resistance to this theory. So the wave theory faced disbelief for two main reasons. First, it contradicted the corpuscular model of light, which was widely accepted. This model was given by Isaac Newton, a towering figure in science. So Newton's influence was so profound that challenging his ideas seemed almost unthinkable. People questioned how someone as brilliant as Newton could be wrong. To put this into perspective, imagine if today a fundamental theory proposed by Einstein was proved incorrect. Given Einstein's immense respect and legacy, many would find it hard to accept. Okay, so that's why wave theory was not readily accepted initially, because corpuscular theory was given by Isaac Newton, and people cannot believe that Newton could be wrong. So here our objective is to understand the initial disbelief surrounding this theory. So the first reason is what we call the medium problem. People at the time believed that all waves needed a medium to travel through. This was a significant hurdle for accepting wave theory. To elaborate, it was commonly understood that waves require a medium. Okay, at that time, electromagnetic waves were not discovered. Okay, so people believed that waves require a medium. For example, sound waves need air, solids, or liquids to propagate. This was a well-established concept. Similarly, water waves need water to travel. This reinforced the idea that a medium is essential for wave propagation, making it hard to imagine how could light be a wave. Okay, so similarly, water waves need water, okay, and sound needs air, solid, or liquid to travel. So people wondered, if light is a wave, how can it travel through space where there is nothing? Okay, so these are the two reasons that made it hard for people to accept that wave theory at first, even though it was actually correct. Okay, so people think that light required medium, but light is coming from sun to earth. There is no material medium in between. So how light is traveling without any medium? So in 1801, scientist Thomas Young proved that light behaves like a wave by conducting his famous interference experiment, which is called Young's double slit experiment. We are going to discuss it in detail in our further lectures. Okay, so Thomas Young proved the light behaves as a wave, because waves interfere. There is constructive interference, there is destructive interference. You may have studied in waves in chapter 11. Okay, so waves interfere or superimpose to give constructive interference or destructive interference. Okay, so Thomas Young proved that light behaves like a wave by conducting its famous interference experiment. It is called double slit experiment. Okay, so he showed the interference of light waves and hence proved that light behaves like a wave. This experiment was pivotal in shifting the scientific community perspective. It showed that light could indeed exhibit wave-like properties, paving the way for acceptance of wave optics. So we are going to explore why light can be assumed to travel in straight lines. This is a fundamental concept in wave optics that help us understand how light behaves in everyday situations. Our objective here is to grasp the reasoning behind the assumption. So let's start by considering the wavelength of visible light. It's important to note that wavelength is extremely small. This small size is crucial in understanding how light interacts with objects around us. For instance, the wavelength of yellow light is about 0.6 micrometer, means 0.6 into 10 raised power minus 6 meter, which is very small, which is much thinner than a human hair. This comparison helps us visualize just how tiny these wavelengths are. Because these light waves are so small compared to everyday objects like mirrors and lenses, light appears to travel in a straight line. Okay, so their wavelengths or their waves are very, very small as compared to objects like mirrors and lenses through which they reflect and refract. Okay, so that's why they appear to travel in straight line. Okay, a beam of light appears to travel in straight line. We cannot see the waves because wavelength of these waves are very, very small. So this is why we can use simple straight arrows known as rays to depict how light travels when it reflects off mirrors or passes through lenses. These rays help us predict and understand light's path. Okay, so this straightforward method of studying light by drawing straight line is called geometrical optics. It's practical approach that works well for many everyday situations. So geometrical optics is effective because it allows us to ignore the wave nature of light in most cases. This simplification is possible due to smallness of the wavelength compared to the objects light interacts with, like mirrors, lenses, prism, etc. Okay, so in geometrical optics, we assume light travels in straight line because of the small wavelength. This assumption is foundational for understanding and predicting light behavior in various applications. So here our objective is to understand the significance of Maxwell's work and its impact on physics. Before the discovery of electromagnetic wave, people thought that waves travel in medium. Waves require medium to travel. Okay, so if medium is not there, then how light wave is traveling in the space? Okay, so this question bothered in scientific community. So even after establishment of wave theory after 1801, people were confused for a long time about how light could travel through empty space. Okay, so it wasn't until the mid 1800s that James Maxwell provided a breakthrough. So this question bothered scientists for about 50 years until James Maxwell came up with the answer in the mid 1800s. So he was studying electricity and magnetism and created some mathematical equations to describe how they work. Okay, so Maxwell equations are not only explained electricity and magnetism but also revealed that light is an electromagnetic wave. This discovery was groundbreaking and provided the answer to how light can travel through empty space. So here our objective is to understand how light behaves and travels through space. So using mathematical equations, Maxwell found something extraordinary about electric and magnetic fields. This is the pivotal moment in physics. So pay close attention as we unravel this discovery step by step. So Maxwell discovered that a changing electric field creates a changing magnetic field. This is crucial because it shows the dynamic relationship between electric and magnetic fields. Imagine it like a chain reaction where one change leads to another, setting the stage for wave propagation. So building on that, the changing magnetic field then creates a new changing electric field. This back and forth interaction is what allows electromagnetic waves to sustain themselves. It's like a continuous cycle that keeps the wave moving forward. So the process of oscillating electromagnetic fields can occur without any physical medium. Okay, this means that electromagnetic waves, including light, can travel through the vacuum of space. Okay, so this changing electric field and magnetic field, these oscillating electromagnetic fields that are perpendicular to each other, and also they are perpendicular to the direction of motion. They can oscillate without any medium. Okay, so they can travel through vacuum also. So when Maxwell calculated the speed of these waves, he found that it matched the speed of light measured by others. This was a groundbreaking realization because it linked light to the electromagnetic waves, suggesting that light itself is an electromagnetic phenomenon. So Maxwell's work led to the incredible conclusion that light is made of electromagnetic waves. This discovery was revolutionary, fundamentally changing our understanding of light and laying the foundation for modern physics. So here our objective is to understand the concept of a wavefront. This is the fundamental idea that will help us grasp how waves behave in different scenarios. To explain a wavefront, we will use an analogy that makes it easier to understand. Imagine dropping a small stone into calm pool of water. Okay, so when the stone hits the water, waves spread out from the point of impact. This is similar to how light waves propagate. Notice the point of impact here, as it's crucial for understanding the origin of wavefront. Let's look at this image of water waves to visualize the concept. Okay, so here is an image of water waves, or in the right side of image it is shown. So what is wavelength? The distance between the crest and trough. What is crest? The elevated part of the wave. You can say what are the water waves. In the left side it is shown actual water waves, or in the right hand side the labeling of water waves is shown. Okay, so the elevated part of the wave is known as crest, and depressed part is known as trough. Okay, and point of source, where stone is dropped in the pond, that is point source, from which water waves are spreading in all directions. Okay, so what is wavefront? So this circular part, one circular part is called wavefront. Okay, so for water waves, what is the shape of wavefront? Circular. Okay, for water waves, the shape of wavefronts is circular. Okay. So as the waves spread, every point on the water surface start oscillating with time. This oscillation is key to understanding how energy is transferred through the medium. Remember, each point is like a tiny oscillator contributing to the overall wave motion. At any given moment, the surface of the water will appear as circular rings where the disturbance is at its peak. These rings represent the wavefronts, showing us the areas of maximum disturbance. It's like seeing the ripples on the water surface. So all points on these circular rings are oscillating in phase. This means they move together, reaching their peaks and troughs simultaneously because they are equidistant from the source. This in-phase movement is a defining characteristic of a wavefront. Okay, so one circular path around these waves, water waves, are in the form of circular ripples. Okay, so one ripple, one circular part is being taken. Okay, on that circular path, all the particles will be oscillating in same phase. Okay, so that in phase movement is defining characteristic of a wavefront. We will define the wavefront with the help of phase difference. So finally, the set of all points that oscillate in phase forms what we call a wavefront. Okay, all the points that are oscillating in same phase is called wavefront. It's a locus of point sharing this specific geometric condition. Okay, what is locus? Locus is a set of all points that satisfy a specific geometric condition. So what is the specific geometric condition in the case of circular wavefronts? That they are at a same distance from the source. Okay, each and every point on the circular path is at same distance from the center, okay, which is equal to radius of circle. So that is the specific geometric condition for circular wavefront. Okay, that all the points that are equidistant from the point source forms the wavefront. Which type of wavefront? Circular in 2D or spherical in 3D. Okay, so that is called locus. So locus is a set of all points that satisfy a specific geometric condition. Okay, so locus of these points which oscillate in phase is called a wavefront. So here our objective is to understand the different types of wavefronts. This will set the foundation for exploring how waves propagate and interact with their environment. So let's start by defining what a wavefront is. A wavefront is the locus of all points that are vibrating or oscillating in the same phase. This means that at any given moment, all these points are experiencing the wave's crest or trough simultaneously. Okay. So now consider how wavefronts move. The speed at which the wavefront expands outwards from the source is known as speed of the wave. This is an important concept because it helps us quantify how quickly the wave energy is being transmitted through the medium. It's also essential to note that the energy of the wave travels in a direction perpendicular to the wavefront. Okay, so propagation of wave is perpendicular to wavefront. Also, we can say energy of the wave travels in a direction perpendicular to the wavefront. This perpendicular movement is a key characteristic of wave propagation and help us understand phenomena like reflection and refraction. Next, we will explore the different type of wavefronts. So the first type of wavefront we will discuss is the spherical wavefront. Imagine a point source like a light bulb emitting waves uniformly in all the directions. This creates a spherical wavefront, which is a common occurrence in nature. Okay, so in a spherical wavefront, the locus of points that have the same amplitude and vibrate in the same phase form spheres. Okay, all the points that are oscillating in same phase, that are equidistant from the point source, forms sphere in 3D. Okay, this is illustrated in the image where you can see a diverging spherical wave emanating from a point source. Notice how the wavefronts are spherical, which is typical for waves originating from a point source. Okay, so you can see in that figure 10.1a, a diverging spherical wave emanating from a point. Okay, in 2D, these wavefronts are shown as circular paths, but in 3D, actually, in 3D space, these wavefronts are like this, in the form of spheres. Okay, so there is a point source, and wavefronts for this point source are like in the form of spheres, concentric spheres. Okay, in 2D, it is being shown in the form of concentric circles. Okay, so figure 10.1, a diverging spherical wave emanating from a point source, the wavefronts are spherical. So here our objective is to understand how wavefront can appear flat under certain conditions. This is an important concept as it helps us simplify complex wave behaviors into more manageable forms. So let's start by defining what a plane wavefront is. Imagine a point source of light emitting waves. At a large distance from the source, a small section of the spherical wavefront can be treated as flat or plane. Okay, if a spherical wavefront is there, or it is very large spherical wavefront, and small portion of this spherical wavefront can be taken as plane. Like we took plane mirror. Plane mirror is a very small part of large spherical mirror. Okay, like this. So we have an illustration to help visualize this concept. Notice how the spherical wavefront, when viewed from a distance, appears almost flat. This is similar to how we perceive the horizon of Earth. Okay, so figure 10.1, at a large distance from the source, a small portion of the spherical wave can be approximated by a plane wave. Okay, you can see a diagram on the right hand side. So there is a spherical wavefront. We have taken a very small portion of spherical wavefront which looks like plane wavefront. Okay, or we can say at very far distance from the point source, the spherical wavefront is very large, and a small part of that spherical wavefront will looks like plane wavefront. Okay, so let's consider the Earth's surface as an example. Although the Earth is nearly spherical, the small area we observe locally seems flat. Okay, just like Earth's surface appears flat to us locally, a small portion of the spherical wavefront can be considered a plane when viewed from afar. Okay, where we are standing, the area, the Earth's surface around us looks like plane surface, but actually Earth is spherical. It is a large sphere. So large spherical wavefront, a small portion, very small portion of a large spherical wavefront can be considered as a plane wavefront. So here our objective is to understand what a cylindrical wavefront is and how it is formed. So let's start by defining cylindrical wavefront. It's produced by a linear source such as long, narrow slit or a line of light. Okay, imagine a line of light emitting waves that spread out in a cylindrical shape. This is important because it helps us visualize how light behaves when it comes from such sources. Okay, so here we have an illustration showing cylindrical wavefronts emanating from a linear source. Notice how the wavefront form cylindrical shape around the source. Okay, in left hand side diagram, you can see there is a linear light source. Okay, it is the light rays are spreading in all directions. Okay, so all the points that are equidistant from this linear light source, the locus of these points form cylinder. So the wavefront formed due to a linear source is of which shape? Cylindrical shape. Okay, in the right hand side of diagram, it is also shown a slit. Slit means a very narrow linear opening. Okay, a very narrow linear opening. Okay, you can take two blades and touch their edges end by end, and then leave small, very small, very thin gap between them. Okay, that forms a slit. Okay, slit is very narrow linear opening through which light can travel. Okay, so that slit will form the wavefronts from that linear source will be of which shape? Cylindrical. Okay, so you can see in this diagram that plane wavefronts are coming from other side, and after passing through this slit linear source, they are becoming cylindrical. Okay, so finally it's important to note that all points on the surface of the cylindrical wavefront are equidistant from the source and share the same phase of vibration. This uniformity in phase is crucial for applications like interference and diffraction, where wavefront coherence plays a significant role. Here our objective is to grasp the fundamental concept behind Huygens principle, which help us understand wave behavior in various mediums. So let's start by defining Huygens principle. It states that every point on a wavefront acts as a source of new disturbance known as secondary wavelets. This concept is essential because it explains how waves can spread out and change direction, forming new wavefronts. Now let's delve deeper into the idea of secondary wavelets. Okay, so every point on given wavefront called primary wavefront act as a fresh source of new disturbance called secondary wavelets. So each point on the primary wavefront generates these wavelets which travel in all the directions at speed of light within the medium. Okay, so these secondary wavelets travel in all directions with the speed of light in the medium. To visualize this concept, take a look at the image showing the formation of secondary wavefronts. Notice how the secondary wavelets spread out from each point on the primary wavefront, creating a new wavefront. This illustration helps us seeing the dynamic nature of wave propagation. Okay, you can see primary wavefront is shown in the figure, and there are 5 points taken on the primary wavefront, from that points secondary wavelets are spreading out. Okay, so after some time, the tangents, the red color line in the diagram, it is a tangent. After some time t, it is tangent taken on one secondary wavelet. Okay, so after taking tangents, drawing tangents on all secondary wavelets after time t and joining these tangents with the curve will give us secondary wavefront. Okay, so tangent drawn on the surface of secondary wavelets will give us secondary wavefront. Okay, so as the secondary wavelets travel, they form a surface that touches them tangentially in the forward direction. This surface represents the new wavefront at any given instant. So finally, the new wavefront formed in the forward direction is known as secondary wavefront. This concept is vital for understanding wave interaction and phenomena such as interference and diffraction. So let's delve into what Huygens principle is all about. It's essentially a geometrical construction that allows us to understand wave behavior. The key idea here is that if we know the shape of a wave at one moment in time, we can use this principle to predict its future shape. Okay, so let's break this down further. If you know what a wave looks like at a specific moment, says time t1, you can use Huygens principle to determine its appearance at a later time t2. Okay, so you can figure it out what it will look like at the later moment t2. So Huygens principle give us powerful tool to visualize and predict wave behavior over time. This understanding is essential for deeper insights into the wave optics. So here our objective is to understand the shape of the wavefront emanating from a spherical wavefront. Okay, so we will use the figure 10.2 to visualize this concept, where F1, F2 represents the spherical wavefront with O at the center at time t equals to 0. Notice how the secondary wavelets create a forward moving wavefront G1, G2. Okay, while the backward D1, D2 does not exist. Okay, so the envelope of secondary wavelets emanating from F1, F2 produces the forward moving wavefront G1, G2. So let's start by identifying the point source represented by O, which emits spherical waves. This is crucial because the point source is the origin of the wavefronts we are studying. Imagine dropping a stone in water. The ripples are similar to these spherical waves. This visualization helps us understand how waves propagate from a central point. So next we focus on F1, F2, which is a portion of spherical wavefront at time t equals to 0. This segment is essential as it serves as the initial wavefront from the secondary wavelets will emanate. Okay, so this is primary wavefront F1, F2 from which secondary wavelets will emerge. Think of F1, F2 as the starting line for our wavefront journey, setting the stage for what happens next. So to determine the wavefront at a later time t equals to tau, we draw spheres with a radius of v tau from each point on F1, F2. This is a critical step because it shows how the wavefront evolves over time. The radius v tau represents the distance the wave travels in time t. So speed of wave is v, and speed into time will give the distance traveled by the wave. Okay, so after time tau, what is the distance traveled? V tau, with v being the wave speed and tau is the time. Visualize this as expanding circles from each point on the initial wavefront. So here we define v, which is the speed of the wave in the medium. Okay, so understanding this variable is important because it influences how quickly the wavefront expands. So as we move forward, let's consider what happens over time if we draw a common tangent to all the spheres. Okay, we have drawn the spheres at each point on the f1, f2 primary wavefront. Okay, sphere of radius v tau. Now, let's consider what happens over time if we draw the common tangent to all these spheres. Okay, as drawn. We can determine the new position of the wavefront at a later time, denoted as tau. Okay, so this tangent represents the boundary where the wavefront has advanced or reached. Now observe the new wavefront labeled as G1, G2 in the diagram. This new wavefront is also spherical, maintaining point O as its center. This illustrates that principle that wavefronts from a point source remain spherical as they propagate. This consistency of the spherical shape is a key characteristic of wavefronts emanating or emerging from point source. Okay, finally let's look at forward envelope or tangential surface. So forward envelope means tangential surface of these secondary wavelets. So denoted as G1 A dash G2. This surface is formed by the secondary wavelets and represented the new wavefront. It's important to note that this forward envelope is what we observe as the advancing wavefront, while the backward wavefront D1, D2 does not exist. This concept helps us understand the directional nature of wave propagation. So here our objective is to understand the construction process, which is crucial for grasping how waves propagate through different medium. So let's start by looking at figure 10.3. The diagram illustrates Huygens geometrical construction for a plane wave moving to the right. Notice the initial wavefront labeled F1, F2 at time t equals to 0. This is our starting point for understanding wavefront propagation. Okay, and A1, A2, B1, B2. What are these lines? Are normals to both F1, F2 and G1, G2 and represent rays. Okay, because ray of light, that is the direction of light propagation, that is perpendicular to the wavefront. So consider a plane wavefront F1, F2 which is moving to the right at time t equals to 0. It's important to visualize this movement as it sets the stage for how the wavefront evolves over time. So next we introduce the concept of the secondary disturbance points such as A1, B1, C1 and D1 by drawing spheres with the radius equals to V tau from these points. What is the V tau? The distance traveled by the wave in time tau. Okay, or by the wavefront in time tau. Okay, so that is V tau. So drawing the spheres with a radius equal to V tau, we can see how the wavefronts change over time as depicted in figure 10.3. Okay, so by drawing a common tangent to all these spheres, we determine the new position of the wavefront labeled as G1, G2 at time tau. This tangent represents the wavefront progression, showing how it moves forward. So finally, we observed that the new wavefront G1, G2 is again a linear wavefront. This reinforces the concept that plane waves maintain their shape as they propagate, a key characteristic of wave behavior in optics. So let's dive into what this shortcoming is. So what are the shortcomings of Huygens principle? So let's see. So again figure 10.2. So the Huygens model has the problem. Okay, so this is the theoretical prediction that wave should travel in both forward and backward direction. But what is the problem here? The backward motion. Huygens doesn't consider the backward propagation of wave. Okay, he told that wave propagates in forward direction only and there is no backward motion. So in reality, we only observe waves only move forward, not backward. Okay, this is a critical point because it challenges the completeness of Huygens principle. Understanding this limitation help us refine our models and improve our prediction about wave behavior. To summarize, Huygens principle suggests wave should move in both directions, but we only see them moving forward. Okay, so our objective here is to understand Huygens explanation of wave propagation at some shortcomings. Okay, so to fix this issue of backward wave, Huygens simply stated without proper explanation that the secondary waves are strongest in the forward direction. Okay, according to Huygens principle, wavefronts are moving in both directions, forward and backward. But wave propagation is only in one direction. Wave cannot propagate in two directions simultaneously. Okay, but Huygens stated without any proper explanation that secondary waves are strongest in the forward direction only. Okay, this was his way of explaining why we don't observe backward waves. So Huygens also stated that these secondary waves have zero strength or amplitude in the backward direction. Okay, he stated that secondary waves are strongest in forward direction and they have zero amplitude or strength in the backward direction. But again, it lacked scientific proof. It was more of a convenient fix than a thoroughly explained phenomenon. Okay, so while this assumption helped explain why we don't see backward waves, why we are not seeing backward waves, this is the explanation given by Huygens, but it is without any scientific proof. It wasn't based on any scientific proof. It was just a convenient fix. Okay, so later when more advanced wave theories were developed, scientists could properly explain why waves don't travel backward. So these theories offered a more comprehensive understanding of wave propagation, filling in the gaps left by Huygens principle. This advancement in wave optics was a significant step forward in the physics. So Huygens was correct about the behavior of waves, but his explanation lacked completeness. As we progressed in our understanding of wave optics, we were able to provide a more scientifically robust explanation for wave propagation. Okay, so let's have a quick recap what we have discussed. So in the 17th century, two main theories of light emerged: Newton's corpuscular theory and Huygens wave theory. These theories laid the groundwork for our understanding of light. So the corpuscular theory proposed by Newton suggested that light consists of tiny particles. However, this theory struggled to explain certain phenomena like interference, diffraction, and polarization. So in contrast, the wave theory proposed by Huygens provided explanation for many light phenomena. This theory was validated by Young's interference experiment, which demonstrated the wave nature of light. Building on the wave theory, Maxwell's theory later described light as electromagnetic waves. This was a significant advancement as it unified the understanding of electricity, magnetism, and light. Maxwell equations are fundamental to modern physics, and we will see how they describe the behavior of light. A wavefront is the locus of all points vibrating in the same phase. Imagine ripples on a pond. Each ripple represents a wavefront where the water molecules are moving together. So three types of wavefronts are there: spherical, plane wavefronts, and cylindrical. Spherical wavefronts are generated due to point source. Plane wavefronts generated from far point source. Okay, and cylindrical wavefronts from linear source. Okay, so Huygens principle states that every point on a primary wavefront acts as a source of secondary wavelets. This principle is crucial for understanding how waves spread and interact. It helps explain phenomena like diffraction, where waves bend around obstacles. So secondary wavelets combine to form new wavefronts in the forward direction. This is a fundamental concept in understanding wave propagation. Imagine these wavelets as tiny ripples that merge to create a large wavefront moving forward. Wave propagation can be predicted by drawing spheres of radius v tau from point on the primary wavefront. Here v represents the wave velocity and tau is the time interval. This method helps visualize how wave move through the space. Next, the tangential surface to these secondary wavelets give us the new wavefront position. Think of this tangential surface as the outer edge of these combined wavelets, marking the new location of the wavefront. Light travels slower in the denser medium, a phenomenon proven by wave theory. This is because denser medium have more particles that interact with the light waves, slowing them down. It's an important aspect of wave optics that affect how we perceive light in different medium. Geometrical optics assume light travels in straight lines due to its small wavelength. This simplification is useful for many practical applications, but wave optics provides a deeper understanding by considering the wave nature of light. Finally, the principle explains forward wave propagation but doesn't account for the absence of backward waves. This is a limitation of model as it primarily focuses on the forward movement of waves. So there are some practice questions. So according to corpuscular theory, when light enters a denser medium, its speed. Okay, so let's start by a question about the corpuscular theory. According to this theory, when light enters a denser medium, what happens to its speed? Consider the options: A increases, B decreases, C remains same, or D becomes 0. Now, next question. Let's talk about a pivotal experiment in the history of physics. Who conducted the famous interference experiment in 1801? What demonstrated the wave nature of light? So consider a point source of light that's very far away. What type of wavefronts does it produce? This concept is important because it helps us understand how light travels over long distances. So moving on, the wavefront produced by a narrow slit source. This is a classical setup in wave optics that helps illustrate how light can spread out and form different patterns. Okay, so what type of wavefront would you observe from a long narrow slit source? Options are spherical, plane, cylindrical, or circular. Next question, let's identify 3 phenomena that Newton's corpuscular theory of light couldn't explain. This is important because it highlights the limitation of the particle theory. Finally, which scientist proved that light is an electromagnetic wave? Your options are Newton, Huygens, Maxwell, or Young. So this is all about wave optics and Huygens principle, introduction to wave optics and Huygens principle. Okay, so I hope you enjoyed the session and understood it well. Thank you.